Well, how are you doing? This is going to be a video about the circle of equal altitude and how it can't work on a spherical surface. Because the circle is a 2D shape, you can't translate that 2D to 3D. Circle of equal altitude is gained by the use of a sextant. You must pre-assume a straight radius, because all radii have to be straight, and obviously all diameters are straight. So you have to pre-assume a straight radius and a straight diameter. And the radius is from the observer's position to the GP of the sun or stars or moon, whichever. The GP is ground position or geographical position of that celestial body. If you're trying to take a 2D, you're basically taking a 2D circle with the observer's distance on the outside of the circle at the circumference, and the GP to the celestial body is at the very center. So your radius is going to be always from the outside of the circumference of the circle to the GP, which is in the center. And the thing about that is that because it's a 2D measurement and it's a 2D, like all distances are given in flat because you're dealing with 2D only. And that's the way they always have given them. So you can't translate, you can't just put that onto a 3D shape like a sphere and expect the distances to translate. They won't. The diameter of that 2D circle of equal altitude will be less in distance than the arc of the sphere that will be residing within it as soon as you put that circle onto that globe. So the distances won't work, and the placements and the coordinates won't work. They'll all be out, they'll all be wrong. So what must be also remembered is you're not just dealing with one circle of equal altitude. There's always going to be two, possibly three, because you're going to always have to find where your position is, and you have to triangulate yourself basically. So that's three circles of equal altitude, and they all could be anywhere between 4 and 10,000 miles each. So you're talking about three different directions where you have distances up to 10,000 miles, between 4 and 10,000 miles in three different directions. All pre-assumed as flat, all with straight radius, straight diameter. It's something that can't be done on a 3D surface. It can only be done on a 2D surface, and the pre-assumption of flat, and all distances are given in flat, and they all work, and they always have worked, and that's the way it's always been done. So that makes a globe Earth model right. So I hope that I'll explain it. I have made a video before this. Hopefully this video will give more of an explanation, and that it will translate better to people out there. I think a lot of people on our opposing side aren't really getting this, but once they do, they'll have to just accept it. It is reality. Okay, thank you. Okay. Okay, so this is how the sextant can't work, right? It needs an angle, and it can't get it off of a curved surface. So it can't work like this. So the only way for them to make it work like this, to work on a spherical surface, the only way you can make it work is by using the center of that spherical surface. But I'll show now in a while why that won't work. So this can't work because you can't get an angle. Even like pre-assuming you can get an angle from here is farcical. You can't. It's already curving. Any curved line won't give you an angle. That's that. It won't give you 90 degrees. But you need to get an angle to a celestial body for the GP, for its GP. So you can't. This would be your radius. You can't have a curved radius. No more than you can have a curved diameter. Has to be straight. So you'd have no choice but to use the center of the sphere and to use a chord treat it as a 2D circle and use a chord through it. So it doesn't work. I'll show in a while why that is just not possible. Okay, both are in two different positions. The reason for that is that once you do it as it's supposed to be done on a flat plane, if you try and translate that onto a spherical surface, you're going to change the placements and the coordinates of the boat, your position. Because here might be a 45 degree angle to the GP of the sun, but when you try and translate that onto a spherical surface, it won't work. Because the diameter, which I show in a few minutes, the diameter here, which will be your chord through the sphere, is going to be less than the arc that's over it. So the two measurements, the distance along your diameter, which will be double your double your radius, is going to be less than the arc over it. So you can't translate them like that. So you're going to have boats in different positions, and your angle also then is going to change. Your angle to the celestial body will change when you start using the center of a sphere as well. So the whole thing changes and it doesn't work. They never have to do any of that. They just use a flat plane and it works all the time. So to get an angle, you need a vertex. So this is your vertex. Is your zenith and your horizontal, your 0 and your 90, right? So that's what you need. And you can get an angle length of 20, 45, 70, 80, 65, whichever you need. But you need that 90 degrees to get an angle, because you need a triangle to get an angle, basically. So this is how it actually works, right? There is your 90 degree angle here, right? Without that, you can't do anything, right? So this is a boat here, and it sees the sun at 30 degrees. This one here sees it at 45, and this one here sees it at 60 degrees. So that's the GP of the sun there. So these are three different distances from the GP of the sun. So there'll be three different radii measurements, and also three different, obviously, diameters, okay? Because you're going to double each one of those radii. So let's say 60 degree one boat here is going to have a radius of, let's say, 2,500 miles. So it's going to have a diameter of 5,000 miles, right? Oh, that's the way it works, right? This one here could be 10,000 miles. This one here could be 8,000 miles, as a diameter. So, so it depends on your angle. But you have to, once you get your angle, right, you start off with you have your vertex, which starts, you have to pre-assume that the angle is starting at the water line underneath the boat. Then you shoot your radius, also known as your zenith distance, to the horizon, and then you take your angle. So you have your angle is to the water, so you have to use a radius, the water as a radius line, and then the water also, the angle has to start there to the celestial body. So the point I'm trying to make here is that once you do that, you have to pre-assume flat. You can't be working with spherical. You have to pre-assume flat. So that's your angle. That's how you get an angle. That's how you use it. Use a sextant, right? So your angle, your initial angle starts with what's known as the horizon dip. So if you're 10 foot above the water on this boat, then you must take 10 foot off of your calculation to calculate to bring your your angle down to the water. So that's how you get your initial radius. Then obviously double that is going to be your diameter. But this is all totally flat, can't be done any other way. So here we have a situation where the boat is here, that's 90 degrees down to here. So there's your right angle, right? There's your other right angle. So you're making a parallel. You're making a kind of your zenith and the zenith of the sun here, right, are going to be parallels. And you're going to then take an angle from the water line underneath your position to that sun. And that's going to give you your angle. And then you will refer to the nautical almanac with your time and your angle. And you're going to find out from that exact time, because the sun is moving, so from that exact time, exactly what distance the sun is from you. So let's say you found out the sun was 2,600 miles, then that means you're going to have a 5,200 mile diameter, because your radius is obviously set 2,600 miles. So you'll have a 5,200 mile diameter, and that means your circle of equal altitude will have a diameter of 5,200 miles. It also means you'll be treating the oceans as one flat plane for 5,200 miles. That's how you have to do it. That's how you have to do it. And that is what that 2,600 miles, that will be your actual distance measurement. You won't be converting that. If you try and convert that to spherical, it won't work. So you will keep it always as flat. But you will also be doing this again 2 more times. Maybe just 1 more time, but often 2 more times, because you're going to be at least making a second circle of equal altitude, because the reason you're doing it is to triangulate your position. And you might need to do a third one. So let's just say you have a second one, and this one is 5,200 miles, your second one is 6,000 miles, and your third one is 10,000 miles. That would be 5,200 miles in one direction, 6,000 miles in another direction, and a 10,000 mile diameter in another direction. So that is 3 different diameters of equal circles of equal altitude from 3 different celestial bodies. And so consequently, that is going to be how do you work those triangles into a spherical surface? You can't, not even by using the center kind of work. It doesn't work like that. The angles are all wrong. As soon as you start going into the center, it changes your initial angles. So you have 3 distances in diameter, radius, and diameter distances that are all pre-assuming flat, and that they are the actual distances you use. You don't change those distances. You don't change any of that. That is what it is. So and it works all the time, every time, and has worked for eons. So the reason it works is because it is a flat plane and not a globe. That's how it works. That's why it works. It wouldn't work if it was a globe. It wouldn't work if it was a globe. You couldn't have pre-assume flat if it was a globe, and it would work. You know, with flat distances, it's a physics impossibility. It's a geometric impossibility, as a matter of fact. So I'm just going to move on from this one. So a circle, right? It has a circumference, a diameter, and a radius. Okay. So radius, any straight line that originates at the center of a circle and ends at the perimeter. Chord, a straight line whose ends are on the perimeter of a circle. A diameter is the longest chord possible. Segment, a part of the circle separated from the rest of the circle by a chord. So a radius is a straight line that originates at the center of a circle and ends at the perimeter. So radius is always a straight line. In geometry, a diameter of a circle is any straight line segment that passes through the center of the circle and whose endpoints lie on the circle. It can also be defined as the longest chord of the circle of a diameter is also called the diameter. So diameter, also a straight line. So radius, any straight line. Diameter of a circle is any straight line, right? Straight line, right? Always straight. No curves. Can't curve a radius, can't curve a diameter. They always have to be straight. Whether you're dealing with a 2D circle or a 3D sphere, right? They have to be straight. Okay. A 2-dimensional shape is a shape that has length and width, but no depth. A circle is one example of a 2-dimensional shape. So a circle is 2-dimensional, always 2-dimensional, not 3-dimensional. Sphere is 3-dimensional, circle is 2. Is a circle 2-dimensional or 3-dimensional? A circle is a 2-dimensional 2D shape, 2-dimensional shape. It only has 2 measurements, such as length and height, and is usually called a flat shape. The ball, however, sphere, is a 3-dimensional 3D shape because it has 3 measurements, length, height, and width, and is sometimes called a solid shape. So a circle is a flat shape, a sphere is a solid shape. Okay? So here is a diagram I've shown before. This is the diameter, right here, this green line here is the diameter of this yellow circle. Okay? This purple line here is the arc length straightened out, right, of this let's say this white dome within the circle. Now, if you can imagine this circle put onto the top of a sphere, that diameter within the yellow circle is going to be less in the distance and length than the straight distance the straightened distance of the arc that resides within it. So the arc will always be, the arc that resides inside the circle will always be more than the diameter of the circle. So if your diameter is 5,400 miles, then it won't translate directly onto here, because the arc could be 7 or 8,000 miles. So you can't use these two opposing points, because here and here in across the arc is not going to be 5,400 miles. It could be 7,600 miles, 8,200 miles. It's going to be more than the diameter. So you can't just put the circle on the circle of equal altitude onto a sphere. It doesn't work. It doesn't translate. The distances and placements are wrong. Coordinates are going to be all wrong, because the coordinates of here and here are not going to translate with here and here when it's put onto this, onto a spherical surface. So here is, let's say, a globe, and here is a circle inside the globe. So treat this as in it's like it's the globe Earth, right? Globe Earth model. This circle here will have a diameter, right? So let's just get this right. So the diameter, right, is going to be I'll go back there a second. The diameter here is going to be less than the arc here, okay? So your arc here is going to be half your circumference, okay? So the polar, if you were to talk about polar circumference, is going to be, we just go here. So 3,950 miles, that's the radius of the polar radius of the globe Earth. So if we then multiply that by 2, we'll get 7,900. Multiply that then by 3.14 will equals 24,806, right, miles. And then we we then divide that by 2. We will get 12,403 miles. So so if we just go back again, so we get 3,950 multiplied by 2, right, will be 7,900. So you'll have a difference of several thousand miles. So this is just, so the diameter of the the diameter of a sphere with a radius, I'm just using the polar radius, so the diameter of the sphere will, with a polar radius of 3,950, will have, I don't know if I should have used the equatorial, it doesn't really matter, will have several thousand less miles than the arc distance. So this distance will be, on the globe Earth, will be 12 to 13,000 miles, whereas within the diameter here will be only 8,000 miles. So, you know, somewhere around that. So you're talking 3,000 or 4,000 miles more. So you can't just plop that circle onto that sphere and expect the straight line diameter that you got by getting the GP of a celestial body, getting the radius to a GP of a celestial body, which will be in the center, and then doubling it for a radius. You can't just expect them distances to work on this arc. It doesn't work. You can't make that happen. It's an impossibility. It's a geometric impossibility, because if that's shorter than the arc, then it can't translate. The two can't coexist. One of them has to be correct. And what one is correct? The one they always use, which is the flat 2D diameter. They always use that. So they never use this arc distance, ever. It's always the flat 2D diameter. So anything to do with putting circles onto spheres is just nonsense. It doesn't work, and it never will. Same here, you have a radius here that is going to be, let's say this radius line here is going to be less than this arc here. So the radius here is always going to be less than the arc, once again. And same here again, radius is going to be less than the arc. Circle of equal altitude. I've renamed it circle of equal angle in my last video on this, just because it may. I'm not trying to change the term. I'm just pointing out that all angles from the outside of the circumference of this circle of equal altitude, all the angles to whatever celestial body that is chosen, will all be exactly equal at that moment in time, right? So this one, they'll all be 50 degrees. All of these are 50 degrees. So everywhere on the circumference of that circle will be a 50-degree angle to the celestial body up here. So so you can call it a circle of equal angle, because angles require straight radius here and straight diameters. So you're going to get an angle, you're going to have to start with a straight radius and then straight diameter afterwards. To get an angle, you have to start with a straight radius though. So you need a 90 degrees straight radius to the GP. There's no way around it. This can't be done on a sphere. It can't be done. It requires 2D. So here we are, circle, there's the sun, the GP of the sun, distance from GP. This is also known as the zenith distance, because your zenith is here, that's the zenith of the sun, there's the GP of it there. So it requires a circle of position, also called circle of position, and this is called line of position, I think. Or one of these is line of position. I get my terms mixed up a bit. But as you can see, it requires 2D. It doesn't work with 3D. It requires 2D. You can't have a curved radius and you can't have a curved diameter. So this is the way it would be worked on a globe, right? Now they would need to treat this here. Let's say the equator line here. They'd need to treat this with a line out here as a radius. Basically, they need to treat this as flat and get an angle using a straight down zenith from the geographic north here and a straight line out here. They would then get an angle from the center to the star here. Now, I'm going to show how this all doesn't work, right, in a few minutes. But why I have this diagram in here is to show this. They have a curved radius and a curved diameter here within this circle of equal altitude. You can't have a curved radius or a curved diameter. It violates geometry. You can't have that. This is supposed to be a 2D surface, and it's been turned into a 3D surface. As soon as you're trying to turn a 2D into a 3D, you can't turn 2D straight distances into 3D distances just by plopping a circle onto a sphere. So this curved radius and curved diameter is not reality. So here, the orange stars, which are up here, are the real star positions, right? Where these red arrows go to, right? The yellow stars, which are these ones, right, are their positions after global conversions. So this is why it doesn't work, right? When you take angles, right, and you treat, you send a direct straight radius out to the horizon, right? And you get a star, right? And you take an angle to the star or celestial body, and you do the same again over here, right? You have two circles of equal altitude. So your one circle is here, there are circles there. These are your two angles to the two stars. When you try and then change that and put these into the center of a sphere, that changes the angles to the stars. You also are going to need straight radius and straight diameter to get angles here. As you can see, this is a straight radius here. These are all straight radius and straight diameter. But you have them on the side of a sphere. But that won't work, as I showed earlier, because the arc that will be here will be more than the diameters. So it won't work. And you have to remember a sphere is 3D. So and on the globe Earth, they have a bigger equator than they have a bigger equator or equatorial radius and circumference than they have polar. So that is because it's an oblate spheroid, so that mutates it even more. So it just can't be done. It's an absolute impossibility. And as soon as you start using the center of a globe, you change the angle to the stars. So this is the person's position. This is the actual angle they got using a 90 degree. But as soon as you start putting them in the center, then their angle to the stars are these purple. arrows here. So the actual angle to the stars they have are these two red lines. But when you start using the center of a globe Earth, you start pre-assuming stuff, then the angle to their angle to the stars change. So they don't have those angles anymore. So if they do calculations using these angles and using flat plane, and using straight line radiuses and radii and diameters, how are you going to translate that onto a sphere when you still need straight line diameters and radii? And you're going to have to be making chords through, treating the sphere as a circle and making chords through it. And then you're going to completely change your whole calculation. You won't know where you are if you have to change it then to, if you're changing then to spherical, putting things into the, bringing lines in and angles in from the center of globe Earth. Your star positions are going to change immediately. So it makes the first calculations you did completely void. It's like you're basically saying this is all pointless here, yet this is the way they always do it, and it always works. But then they pre-assume that they're on a globe and they start doing this. But this is after they've done this. They think that they can do that, but they can't. Like these angles to this star and this star, they're never used. It's only this is used. But there's the pre-assumption that they're using the center of a globe and it all works out the same. It would be the same angle. It wouldn't. If you're using a flat plane or the center of a globe, then the angles are going to be different. The angles you have to the stars are going to change. They're not going to be the same. So there's another thing that doesn't work. You'd have to completely change the angles, which would make the whole thing pointless. You wouldn't even use it. If we were on a globe, a sextant wouldn't exist. There'd be no point to it. It wouldn't work. Because they can't use it. How are you going to get two or three circles of equal altitude on a globe? You can't even get one. And as soon as you do start putting them on a globe, it's going to change the angles. Because as you can see here, the angles are here and here. As soon as you change here to the center, as soon as you start putting lines from the center of a globe, the angle widens out the stars. Your angles down. It just doesn't work. It's an impossibility. Circle of equal altitude, that's what it has to be like. They're all 60 degrees. It has to be 60 degrees all around. You can't have curved radii. You can't have it. Okay, this one here, this is not mine, this is just one I picked up. I just want to point out some things. They're using nautical miles here, right? So that's 3,000 nautical miles as a radius, right? They have a curved radius line here and a curved diameter. So that's a 6,000 mile curved diameter, right? That's an impossibility. You can't have a curved radius and a curved diameter. And look here, these are not angles. None of these are proper angles, and they're not all going to be the same. It's a complete mess, and that's only one. Why don't you try to do a second one? I mean, you can with a 3D program, you can do this and you can stretch out the circles and do all this other nonsense. But you can't do that in reality. In reality, they use flat surfaces because that's what reality is. They're using flat. They're using 2D flat because this is what a circle of equal altitude is. It doesn't work any other way. So there is no way out of it. Circle of equal altitude requires flat 2D. It can't work on a curved surface. It would change all the angles to the stars. You couldn't have any radii, or you couldn't have any diameters. Nothing would work. So the whole thing is just a mess after that. Okay, thank you.